oxygen consumption and resting metabolic rate. Alright, so the equation that we're going to be working with for oxygen consumption is the equation on the top here. We're going to have the inspired volume of air multiplied by fraction of inspired oxygen minus the volume of expired air multiplied by the fraction of expired oxygen. Okay, and then this equation is the equation that we get from the Haldane transformation, and this is the equation that we're going to be using. Okay, we have VO2 equals expired volume multiplied by 1 minus fraction of expired CO2 plus fraction of expired O2 divided by 0.7904. All of that multiplied by the fraction of inspired oxygen, which is 0.2093, minus fraction of expired oxygen. We're also going to be calculating CO2 production, which equals expired volume multiplied by the fraction of expired CO2, and then the respiratory exchange ratio, which is equal to carbon dioxide production divided by oxygen consumption. One important thing to note here as you're going through these equations is that O2 and CO2 are going to be reported as fractions, not as percents. So even though in lab you might be measuring them as percents, make sure you're putting them into the equations as fractions. Okay, the volume of air that we're going to be using in these equations need to be in STPD, and we will be sampling them at ATPS. So it's important that we multiply the volume of air that we measured by the STPD correction factor. Okay, so this is the equation for the STPD correction factor. And again, we'll be getting water vapor pressure from a table in the lab manual. That's table 15.6. And volume in STPD is simply the volume of air that we measure, which is ATPS, multiplied by the STPD correction factor, which we'll be calculating. And that's based on, again, ambient air conditions. And the expired volume in ATPS will equal the volume that is pulled out of the Douglas bags by the analyzers minus the dead space volume plus the dry gas volume, which is what we will be measuring. Okay, so for our example, we have a 70 kilogram male, and the gas that was in the Douglas bag was analyzed for 30 seconds. The analyzer that we use pulls air out of the bag at a rate of 300 milliliters per minute. So then we know that the amount of air that was analyzed was 150 milliliters. The dead space that we're going to have is 150 milliliters. And the dry gas volume that we measured from the Douglas bag is 15 liters. And fraction of expired oxygen is 17%. Fraction of expired CO2 is 3.6%. The ambient air temperature is 22 degrees Celsius. Barometric pressure is 740 millimeters of mercury. And water vapor pressure is 20. All right, so to get the expired volume in ATPS, we have 150 milliliters, which is the air that was sampled by the analyzers. And then we would subtract the dead space, which also happens to be 150 milliliters, plus the volume that we measured. Okay, and calculating the STPD correction factor. So that equals 0.877. All right, so in order to go from expired volume in ATPS to expired volume in STPD, we'll take 15 liters multiplied by the STPD correction factor, which is 0.877. And so our expired volume in STPD is 13.15 liters. Okay, so now we have all the numbers that we need, so we will plug these numbers into the equation for oxygen consumption. .15 liters times 1 minus Okay, and that gives us an oxygen consumption value of 0.529 liters per minute. Okay, and in order to get CO2 production, we take expired volume of air multiplied by fraction of expired CO2. And that gives us 0.473 liters per minute. Okay, and one extra thing to note is these values are in liters per minute because we sampled our the subject breathed into the bag for exactly 1 minute, so we know that that has to be liters per minute. The last thing that we're going to calculate here is the respiratory exchange ratio, and it's simply carbon dioxide production divided by oxygen consumption. That gives us a value of 0.89. Okay, so just one last thing to note is just make sure that you go through this equation, and now you have an idea of what numbers sort of make sense, so that when you go through it on your own, you'll kind of have an idea of whether or not you're on the right track.